We'll start in 1 minute. We'll continue in section 7.4, integrals of rational functions by partial fractions. If there's time, we'll start section 7.5 on strategy for integration. We were discussing case 3 of the partial fractions method. So in this case, the denominator q of x has irreducible quadratic factors, none of which are repeated. So an example of an irreducible quadratic factor has the form ax squared plus bx plus c, where the discriminant is negative. b to the second minus 4ac is negative. And this example is an example of an irreducible quadratic factor, x squared plus 4x plus 10. In other words, it cannot be factored over the real numbers. So if our denominator has one irreducible quadratic factor, then the partial fraction decomposition includes this expression, ax plus b over lowercase a x squared plus bx plus c. Okay, in this example, the indefinite integral of x squared plus 2x plus 1 over x minus 1 times x squared plus 9. We do have one linear factor, x minus 1, but x squared plus 9 is an irreducible quadratic factor. So we want to find simpler fractions to represent this. So for corresponding to the linear factor x minus 1, we have a over x minus 1. And for the irreducible quadratic factor x squared plus 9, the numerator has the form bx plus c. So we want to find the values of a, b, and c. So we'll rewrite the sum of these two fractions as a single fraction with the common denominator. So we multiply a over x minus 1 by 1 in the form x squared plus 9 over x squared plus 9. So a over x minus 1 times x squared plus 9 over x squared plus 9. We multiply the other fraction, bx plus c over x squared plus 9, multiply this by 1 in the form x minus 1 over x minus 1. So bx plus c over x squared plus 9 times x minus 1 over x minus 1. Okay, then we can add the fractions because they have a common denominator. x minus 1 times x squared plus 9 in the denominator. So in the numerator, let's see, we'll have a times the quantity x squared plus 9. So that's ax to the second plus 9a. And then the quantity bx plus c times x minus 1. We're going to get bx times x, or plus bx to the second. And then plus cx minus bx. And lastly, minus c. Okay, so let's collect like terms. Let's just focus on the numerators. This numerator, ax squared plus 9a plus bx squared plus cx minus bx minus c, this has to be equal to x squared plus 2x plus 1. So we can just work with the numerators, x squared plus 2x plus 1. And we'll combine like terms. We have ax squared plus bx squared. We'll write that as a plus b quantity times x squared. The terms with one factor of x, cx minus bx, we'll write that as plus the quantity c minus b times x. And then the constant is positive 9a minus c, so plus 9a minus c. Okay, the coefficient a plus b, the coefficient of x squared, those have to be equal. So 1 has to be equal to a plus b. I'll write that as a plus b equals 1. And the coefficient of x on the left is 2. The coefficient of x on the right is c minus b. So c minus b has to be equal to 2. And the constant 1 has to be equal to 9a minus c. So 9a minus c equals positive 1. We have 3 variables, a, b, and c, and 3 equations. So, and the equations are independent, so we will be able to solve for a, b, and c. So I suppose what I'll do is I'll solve the first equation for a. We get a equals 1 minus b. And then in the third equation, I'll replace a with 1 minus b. So I get 9 times the quantity 1 minus b minus c equals 1. Or 9 minus 9b minus c equals 1. 1. Subtract 9 from both sides, and I get negative 9b minus c equals negative 8. Okay, so let's use this equation, negative 9b minus c equals negative 8. And this equation, c minus b, together in a system of 2 linear equations. Okay, so c minus b equals 2. And for convenience, I'll rearrange these numbers. I'll write negative c minus 9b equals negative 8. And then when we add these 2 equations, C plus negative C is 0. Negative B plus negative 9B is negative 10B. On the right-hand side, 2 plus negative 8 is negative 6. And so the value of B is negative 6 over negative 10, or positive 3/5. And now we can find A and C. We have this equation, A equals 1 minus B. And since B is 3/5, A is 1 minus 3/5, which is 2/5. So that's the value of A. And we can solve for C using this equation. C minus B is positive 2. And since B is 3/5, we can write C minus 3/5 equals 2. And then add 3/5 to both sides. We get C equals 13/5, because 2 plus 3/5 is 13/5. Okay, so we can write the integral, where the integrand is a sum of the two simpler fractions using A, B, and C. So we'll do that in the next step. So A over x minus 1, I'm going to replace A with 2/5. Over x minus 1. And then the value of B is 3/5. I'm going to write the next, instead of the entire bx plus c over x squared plus 9, I'll write it as two terms, each having a denominator of x squared plus 9. So 1 with B equals 3/5 x, so 3/5 times x over x squared plus 9. And then the other one, the value of C is 13/5, so we write 13/5 over x squared plus 9, and then dx. Okay, I think I'll leave the rest of this for you to do. We've seen how to integrate terms like this. I'll just mention briefly the integral of the term on the left, 2/5 over x minus 1, involves the natural log. For the integral of the middle term, you can use the substitution rule, where u is x squared plus 9 and du is 2x dx. And then for the integral of the term on the third term on the right, this will involve inverse tangent. So you can use a trig substitution. You can assign x to be 3 times tangent of theta, and then go through the process of integrating that. Do you have any questions on how to proceed with that one? Okay, let's look at the next example. But first, we will discuss the case 4 for integration by partial fractions. So case 4, the denominator q of x has repeated irreducible quadratic factors. So suppose q of x has the irreducible quadratic factor the quantity ax squared plus bx plus c raised to the power m. And so the partial fraction decomposition will include m terms. Notice that the first term is the quantity ax squared plus bx plus c to the first. The second term has a denominator for it's the quantity of ax squared plus bx plus c to the second, and so on. And then each of the numerators is of linear form. The first numerator, a sub 1 times x plus b sub 1, and so on. Okay, so in this example, it doesn't take much to get a fairly complicated case 4. This is about as simple as you're going to ever get, but it's still going to be quite a lot of tedious work involved. So we do have one linear factor, which is just x, and x squared plus 2 is irreducible, and it's raised to the power 2. So our partial fraction decomposition for the linear term x in the denominator, we write a over x. And then for x squared plus 2, the numerator for this, I'll write it as bx plus c. And then we also have a denominator with x squared plus 2 quantity squared. The numerator for this is dx plus e. So we need to find those 5 numbers, a, b, c, d, and e, and then afterwards we'll integrate, or at least set up the integral. So if it's okay, let's just focus on the numerators. Well, I'll go ahead and do a little bit more detail. So the original rational expression, 4 over x times x squared plus 2 quantity squared. So we want to multiply a over x by 1. So the form that 1 takes will be x squared plus 2 quantity squared over x squared plus 2 quantity squared. We want this denominator to be the same as the denominator of the fraction on the left. Okay, then we'll multiply the middle term by 1. Bx plus c over x squared plus 2. What form will 1 take this time? Well, we need another irreducible quadratic factor because the least common denominator has 2 factors of x squared plus 2, and we also need the linear factor x. So if we multiply by 1 in the form x times x squared plus 2 over x times x squared plus 2, and then the third term, dx plus e over x squared plus 2 quantity squared, multiply by 1. What form does 1 take for this one? Yeah, x over x. So that's the easiest one. And now we have a bunch of tedious algebra and arithmetic. So we might as well get started. Now let's just focus on the numerators. since the fractions have a common denominator, the sum of the numerators has to add up to 4. Okay, when we square the quantity x squared plus 2, we get x to the 4th plus 4x squared plus 4. Well, for the next one, I guess we should do it in 2 steps so we don't skip too much. Let's go ahead and multiply x times the quantity x squared plus 2, so we get the quantity x to the 3rd plus 2x. And then on the right, dx plus e, multiply that quantity by x, we get plus dx squared plus ex. And distribute multiplication by a, so we get a times x to the 4th plus 4a times x to the 2nd plus 4a. And then for the next product, bx times x to the 3rd is b times x to the 4th plus c times x to the 3rd plus bx times 2x is plus 2b x to the 2nd. And then plus c times 2x is plus 2cx. And then plus dx squared plus ex. Okay, in the next line, we can combine like terms. We have ax to the 4th plus bx to the 4th. We'll write that as a plus b, quantity multiplied by x to the 4th. There's only one x to the 3rd term, so plus c times x to the 3rd. And then we have the x squared terms. So the coefficient of this x squared term is 4a. The next x squared term has a coefficient of 2b, so plus 2b. And then plus dx squared, so plus d, and this quantity multiplied by x squared. Okay, then the x terms. So there are 2 x terms, 2cx plus ex. So we'll write this as plus the quantity 2c plus e times x. Then there's a constant. There better be, because it has to simplify to a constant. Okay, so the only constant is 4a. Okay, so now we can jettison the variable terms in that equation and write down equations that correspond to coefficients. So what's one equation I can write down? Okay, notice on the left-hand side, we just have the constant 4. There isn't an x to the 4th term on the left-hand side. On the right-hand side, we have the quantity a plus b times x to the 4th. So what must that mean? Yeah, it must be the case that a plus b is 0. There's only one x to the 3rd term on the right-hand side, but the left-hand side doesn't have an x to the 3rd term. So this one is pretty nice. This has to mean that c is equal to 0, right? The left-hand side does not have an x to the second term. So that means on the right-hand side, the coefficient of the x squared term has to be 0. That is 4a plus 2b plus d equals 0. The left-hand side does not have an x term. So that means on the right-hand side, the coefficient of x has to be 0. So the coefficient 2c plus e is 0. And then the constant on the left-hand side is 4. That's equal to the constant on the right-hand side, 4 times a. Okay, so we know that c is 0. What else do we know? Yeah, a equals 1. If 4 equals 4 times a is equal to 1. So somebody online type in something else that we can deduce from what we've done so far. Hey, nobody online. Anybody in class? Which one? Yeah, e is 0. Since c is 0, e must be 0 also. Did I hear you right? Okay. Since a plus b is 0, yeah, I got someone to type in what that is. Since a is 1, 1 plus b is 0. That means b is negative 1. And now there's only d to find. So if we replace a with 1, 4 times 1 is 4. Replace b with negative 1, so plus 2 times negative 1 is 4 minus 2 plus d. Or 2 plus d is 0, so that means d is negative 2. Okay, we have everything we need to know to proceed. So we can write down the integral. So we'll compute the indefinite integral of a over x, but a is 1, so that's 1 over x. The value of b is negative 1, and the value of c is 0. So for the next term, the numerator is just negative x over x squared plus 2. But here I'll write it as minus x over x squared plus 2. The value of e is 0. D is negative 2, so this will be negative 2x. I'll write it as minus 2x over quantity x squared plus 2 squared dx. Okay, so this is fairly simple to evaluate. So we get the natural log of the absolute value of x. So we might as well complete this one. The indefinite integral of 1 over x is the natural log of the absolute value of x. For the middle one, we can use the substitution rule. If u is x squared plus 2, then dx is, I should say, du is 2x dx. So let's put in another step. I'll write this as minus 1/2 times the indefinite integral of 2x over x squared plus 2 dx. And the next one is all pretty much all set up for us. Minus the indefinite integral of 2x over the quantity x squared plus 2 squared dx. Okay, so this middle integral, it has the form, it's the integral of du over u. So this just becomes the natural log of x squared plus 2. And what about the integral on the right? So if we let u be x squared plus 2, then du is 2x dx. So this has the form, it's the integral of du over u to the second. So what's the integral of du over u to the second? Yeah, negative 1 over u to the first. Is that what you said? And then we replace u again with x squared plus 2. All right, so what we're doing is we're subtracting a negative, so that means we're going to add 1 over x squared plus 2, and then plus c. Okay, that wasn't too bad. On the next page, we've covered the 4 cases. So here's just sort of a random selection. The indefinite integral of the rational function, the numerator is 4x to the third plus 18x squared plus 9x plus 11. The denominator is 2x squared plus 9x plus 4. So what's the first thing to do on this one? Yeah, since the degree of the numerator is 3 and the degree of the denominator is 2, it's an improper rational expression. So before we do any integrating, we have to divide the numerator by the denominator using polynomial long division. So we do that first. Divide 2x squared plus 9x plus 4. Divide that into the numerator, 4x to the third plus 18x to the second plus 9x plus 11. So 2x squared goes into 4x to the third, 2 times x times, and then multiply 2x times the quadratic expression. We'll get 4x to the third plus 18x to the second plus 8x. And then subtract 4x to the third minus 4x to the third is 0. 18x squared minus 18x squared is 0. 9x minus 8x is x, 1x. And then we have this plus 11. So we cannot, this is working. We're done with the long division. So the definite integral will be equal to the quotient 2x, I should say the integrand of the indefinite integral becomes 2x, and then plus the remainder, x plus 11, over the divisor, 2x squared plus 9x plus 4. dx. We can easily find an antiderivative for 2x. That's just going to be x squared. And we can use partial fractions to find the integral of this proper rational function, x plus 11 over 2x squared plus 9x plus 4. Okay, so let's do the work on that. X plus 11 over 2x squared plus 9x plus 4. The denominator factors pretty nicely. So we can just grope a little bit to find the two factors. So both has to have a plus sign. And it looks like 2x plus 1 times x plus 4. The denominator has two linear factors, so the partial fraction decomposition will have the form a over 2x plus 1 plus b over x plus 4. And we can add the two fractions by finding a common denominator. So we're going to multiply a times the quantity x plus 4. So we'll get ax plus 4a. And then b times 2x plus 1. So we get plus 2bx plus b. Okay, so the numerator x plus 11 has to be equal to this numerator. So x plus 11 equals, let's combine like terms, ax plus 2bx, so we have the quantity a plus 2b times x. And then the constant 11 corresponds to plus 4a plus b. Okay, what are the equations we get? We want to find or determine the values of a and b. So what's one equation without the variables? I should say without the variable x. A and b just represent constants. So type in one of the equations we get based upon the fact that the polynomial x plus 11 is equal to the polynomial a plus 2b times x plus 4a plus b. Okay, a plus 2b equals 1. That's one of them, the coefficient of x. So in general, I guess I was assuming something. In general, if two polynomials are equal, then the terms, individual terms, have to be equal. So 1x has to be equal to a plus 2b times x. So a plus 2b equals 1. And the constants have to be equal. 4a plus b has to equal 11. So all we have to do now is solve this system. I'll leave the top equation the way it is, a plus 2b equals 11. And then I'll multiply every term on both sides of the bottom equation by -2. So we get negative 8a minus 2b. Sorry about that. That should be a plus 2b equals 1, not 11. On the bottom equation, multiply both sides by -2, so the right-hand side is -22. Okay, then when we add these, the constant b cancels, and we get -7a equals -21, so a is equal to +3. And if a is +3, well, we'll use that equation. 3 plus 2b equals 1. That means 2b equals -2, and so b is equal to -1. Okay, so our integral that we want to evaluate is the integral of 2x. The value of a is 3, so 3 over 2x plus 1. And then minus 1 over x plus 4 dx. Okay, I'll leave the rest of that for you to do. For now, let's bypass this last example and at least do the intro to section 7.5. Section 7.5 is essentially a review of the first 4 sections. So I've assigned, for practice, I've assigned these 10 exercises from section 7.5. Okay, another important thing, important for this class anyway, on page 503 of the textbook is a table of basic integration formulas. And you should be familiar with all of them, or at least know how to derive them. So work hard on memorizing these. And if you haven't already, you'll notice that some are similar to others and follow similar patterns, which helps you with the memorization. But yeah, you need to know those basic integration formulas by heart. As you have seen and have probably experienced for yourselves, different integration strategies sometimes work when evaluating a particular integral. So here's a brief list of the integration strategy given in the textbook. Simplify the integrand if possible. Look for an obvious substitution. Classify the integrand according to its form. If you come up empty, then try again. So one thing you can count on, if there is a problem in the textbook, it can be solved. So if you fail at solving it the first time, then try again. Hey, we have reviewed or learned These, so far this semester, the substitution rule, which you saw in Calculus 1, we reviewed that in section 7.1, integration by parts. Section 7.2, the trigonometric integrals. In section 7.3, trigonometric substitution. And then the latest from section 7.4, partial fractions. Okay, so we'll get started on the first example from section 7.5. So on the following pages are integrals to evaluate by whatever means we like. So let's get started on this first one. Okay, the indefinite integral of dx over the square root of x plus x times the square root of x. Okay, so does anything come to mind on how to start or what to do to get started? Well, we can get this to work out if we just make a substitution. If I assign u to be the square root of x, which is the same as x to the 1/2, and du turns out to be 1 over 2 times the square root of x dx. In our indefinite integral, we see dx. So we want to solve this equation for dx, but remember that we're replacing the square root of x with u. So I'll do this in a couple of steps. Let's multiply both sides by 2 times the square root of x. So we get 2 times the square root of x du equals dx. But we use our substitution, u equals the square root of x, so we write this as 2u du equals dx. Okay, so let's write that in the numerator. Replace dx with 2u du. And what will the denominator become based upon the substitution u equals the square root of x? The term on the left in the denominator is pretty obvious. That is the square root of x, so we replace that with u. And what about x times the square root of x? Yeah, it's going to be u to the third. Since u equals the square root of x, u squared equals x. So this term is u squared times u, or u to the third. Okay, what should we do now? So now we remember one of those steps in the integration strategy. Simplify the integrand if possible. Both the numerator and denominator have a common factor of u. So if we cancel one common factor of u, we'll just be left with the indefinite integral of 2 over 1 plus u squared du. You can think of this, if you want, you can think of this as 2 times the indefinite integral of 1 over 1 plus u squared du. And we've seen this kind of indefinite integral a few times. You might be able to just tell me what that's equal to. 2 times Yeah, 2 times the angle whose tangent is u, the inverse tangent of u, right? If you don't remember that, you can derive it by using a trig substitution. You can assign u to be tangent of theta, 1 times tangent of theta, and so on. But we have to remember that u is our temporary substitution, so we replace u with the square root of x. So that's all there is to that. Okay, we're about out of time, so online, go ahead and sign in for attendance. We'll continue in section 7.5 on Monday. Nicholas. Sarah. Okay, have everyone.